There are two types of forces, contact and non-contact. For contact forces, let us start off with the familiar one, which is actually your reaction force. So when an object sits on the ground has a reaction force on the object. Tension is another contact force. Then we have the spring force, where the force exerted on the spring is equal to K multiplied by X, where X is actually the extension. So this formula only works within the limit of proportionality. Beyond which, beyond the limit of proportionality, the spring is no longer, beyond the limit of proportionality, the spring is no longer elastic. Next category is the resistance force. So one form of resistance force is the friction. When an object is moving, the frictional force is acting against the object which is in contact on the ground. So the frictional force in this case is equal to mu n. Mu is actually again another proportionality constant, and n in this case is the reaction force. Next is viscous drag force. Viscous drag force occurs when an object is being dropped in the air or a fluid, and the viscous drag force acts opposing the motion of the object. And Fr is equal to Kv. K again is the proportionality constant, while V is actually the speed of the object. Next one to look at is actually your upthrust. Upthrust occurs when an object is submerged in a fluid. So the upthrust is equal to V rho g. V is the volume of the fluid that has been displaced. Rho is the density, and g is the acceleration due to gravity. The final formula to look at is when we calculate fluid pressure, where P is equal to H rho g. H is the depth from the atmospheric pressure, rho is the density of the fluid, and g is the acceleration due to gravity. For non-contact forces, there are three, specifically gravitational force, electrostatic force, and magnetic force. All these sets of formulae will be subsequently taught in the other topics. Let's study now the motion of an object, and there are three possible cases to be tested at the A level. In the first case, object is undergoing translational motion, which means the object is undergoing one-dimensional or two-dimensional motion, and the object is not rotating, since the summation taught is equal to 0. This is the case whereby we have earlier illustrated with quite a number of examples. In case 2, object is undergoing rotational motion, and the object is actually stationary. It doesn't move or doesn't translate. So you can see that in this case, the summation, the net force acting on the object is 0. So for example, we actually have a ruler pivoted at the CG with a length of 2L. If you apply a force upward here, F, and a force downward here, F, the net force would be 0 because these two will cancel each other. And the torque would have been 2 times FL, and the direction would be clockwise. So this is a pure rotational motion. Let's take a look at the third case, static equilibrium, where the summation torque is 0 and the net force is 0. The example that we're going to look at is actually a ladder with a length L, angle theta, all right, sitting on one side the wall, the other side the ground. And if you were to study the forces acting on the ladder, there will be the weight exerted at the midpoint, all right, L/2, exerted at the CG, all right, of the ladder, and the length here will be L/2, here will be L/2 as well. There will be two reaction force acting perpendicular. One is as a result of the wall acting on the ladder. The other is a result of the reaction force from the ground acting on the ladder. And last but not least, there will be frictional force. To determine the direction of the frictional force, there's a couple of ways to do it. By looking at W, MB, and NA acting on the ladder, we know that NA is the only horizontal force. If that's the only horizontal force, rightfully the ladder will be could be translating horizontally. So in order that the object is at static equilibrium, the frictional force acting on the ladder by the ground must be in this direction to actually cancel the reaction force NA. Finally, since the weight will cause the ladder to slip, you will find that the frictional force acting on the ladder by the wall will be actually upward. Typically, to solve this question mathematically, we can then work out 3 equations based on this. First, we have a convention xy labeled as positive. So for summation fx to be 0, your NA and your FG has to be equal. Next, if you look at the vertical force, summation of the vertical force, then your NB plus your FW must be equal to your weight. Finally, we'll take a principle of moment about point W. It could be W or at this point. Say if you take the principle of moment about W, the moment of FW and NA will be 0, and W and FG will be a clockwise motion because it's causing the ladder to move clockwise, while this will move the ladder anti-clockwise. So this will be moving this direction, both these will be moving this direction. So let's take a look at the moment caused by W. In this case, it will be W multiplied by this perpendicular distance from the pivot to its line of action. So in this case, this will be the distance, perpendicular distance. And since this is L over 2, this will be L over 2 cos theta. This will also be L over 2 cos theta. Hence, the clockwise moment caused by W is W times L over 2 cos theta. This is the perpendicular distance. The next one, if you look at the FG line of action is in this direction. Therefore, the perpendicular distance will be from the pivot to here. So this will be L sine theta. So it's FG multiplied by L sine theta. Finally, if you look at MB, which is actually the anti-clockwise direction, the perpendicular distance will be from the point here to actually at this point, which is actually the distance of this. So hence the anti-clockwise moment will be MB multiplied by L cos theta. Finally, let's now represent the resultant reaction force with RW, which is actually a vector summation of your FW and your NA. Likewise, let's take a look at the resultant force acted on the ladder by the ground. In this case, it will be a vector summation of FG and MB. If we have three coplanar forces acting on an object which is at static equilibrium, then the line of actions of all these forces must all coincide at one point. And in this case, it is coinciding at this point here. All right. The reason for that is that if you were to take principle of moment about that point, then the net torque must actually be 0.